second morning session with the talk of a scientist from Nice. His name is frisch. So, 1 hour. 1 hour at least. But not more than that.
Okay, I'll try to do it in 1 minute. Is this also changing the? Is this just a laser, or is it also supposed to operate this way?
So it is a laser left, yeah? I think so. It's not steering anything, no.
Yeah. Okay. The laser is this one.
Yes.
Fine. Yeah. I do it. All right. Hello, everybody. So now we're going to hear a little bit of beyond. You know, this is not just publicity and alpha effect and so on. So I decided to speak about a somewhat different subject for two reasons. One is that I have not been involved in things helical since, maybe 6 or 7 years ago with Zheligovsky and Potolina. And we showed that gate separation, modest gate separation is useful and things like that, but it wasn't, it was mostly eddy diffusivity, so not, there wasn't really marginality. Also, I don't want to tell you about the great things I've done 40 years ago. Okay, that's understandable. I could have given a historical talk about other people's work, particularly about the key contribution of Krajnan regarding cascades in their direction. But that will be present marginally in what I'm going to say. And then I assumed that given that Excel is a numerical type, and an attractive numerical type who attracts other numerical types, there must be a significant percentage of numerical types in this room. And what I have to say is of some importance for those guys and girls. Okay. So I will start with an observation which is probably rather familiar with if you have done a lot of simulation, particularly by spectral or pseudo-spectral methods. You may have noticed, or you have been told, that if you do a hydrodynamical type, that includes MHD, of course, simulation, and you don't have enough resolution, or your dissipation is too small, it's basically the same thing, then you get weird phenomena. Frequently people say, oh, truncation effects become severe, and it must be one of these Gibbs phenomena, or related to the Gibbs phenomena. As you will see, this is not true. It's a completely different thing. So, I'm going to address the basics of what happens when one considers a hydrodynamical situation with a finite, perhaps very large, finite number of modes, dissipation at all, and, which is the extreme case. And then you will see something very, very unexpected is happening. But it also turns out that what we discovered, there's the list here, Shamriti Shankarai, who is now in Nice, is a former student of Rahul Pandit in Bangalore, Sergei Nazarenko, many of you know him. He used to be in the Soviet Union a long time ago, he's now in Warwick. And Takashi Matsuko from Kyoto. So the things that we discovered actually are part of a respectable area of intellectual research of, I wouldn't say humanity, but the scientists. Part of which goes back very far. So let me go to the time of Galileo. Before Galileo, you had this rather common vision that you have things of the celestial realm, the heaven, which were envisaged as permanent. Permanent either in the trivial sense that nothing changes, or that things change periodically. Then you had the sublunar or earthly domain where things were changing, decaying, etc. Very different. Because here on Earth, evil forces, the devil and so on, that act rather strongly, and of course not up there. And then Galileo discovered the sunspots. And it was immediately obvious that they are decaying. That is not permitted. You see? Now, if you look at it from a more modern point of view, you can say most things heavenly are conservative, or to be a bit more technical, Hamiltonian. Whereas down here, when we play with water and so on, hydrodynamics, dissipative, not conservative, at least not conservative of energy. So, and as you will see, the game about which I'm going to talk, they mix conservative and dissipative things in a novel way. But I must say that I've been obsessed by this question for a very, very long time. So now I'm going to move not to the Galileo's time, but 1966, which was roughly the year of invention of the alpha effect. And I was at the Courant Institute, and I had a lot of interaction with Mandelbrot and other people at that time it was Beldat. It was one of the best places for doing research in the United States. I was not visiting the Beldat officially, but actually I was spending a lot of time there. And there was a group of 4 or 5 scientists who met every week trying to do something about the following question. Is statistical mechanics, equilibrium statistical mechanics, and thermodynamics in particular, can it tell us something about turbulence? That's a tough question. We didn't go go very far at all. Actually, they basically got nowhere. Also, at that time, we did not have a full understanding of all the things that had already been done. So, now, here I want to introduce a nice gentleman who are connected with the field I'm going to talk about. Eberhard Hoff, a mathematician, Sundar Lee, a physicist who even has a Nobel Prize. Together with Young, he got a Nobel Prize for broken parity invariance. And some people have noticed that parity invariance, helicity, Pasteur chirality, and all these things perhaps have something in common. I mean, certainly broken parity invariance. But of course, TDD did a lot of other things. And finally, Robert Crichton, who died about 2 years ago, no, 3 now, yeah, 3 years ago, and you will see how the story unfolds. So let me see if I'm able to go to the next page. The arrows are here. It worked splendidly. Okay, most of these things saved. Now, in 1952, independently, Hopf and Lee applied some kind of equilibrium statistical mechanics to the 3D Euler equation, incompressible Euler equation. They didn't do exactly the same thing, but they both came up with an energy spectrum proportional to k squared, which is just an equipetition of energy among all Fourier modes. Because of the volume element, which is proportional to k squared, you then get a k squared spectrum. Now that can have had most people laughing, because in 1952, people doing turbulence knew that things were, if not exactly Kolmorov's k to the minus 5/3, pretty close to that. So one goes this like this, the other one goes like that. Didn't make a big splash. And then, quite a number of years later, in 1967, some of the machinery used by TDD and reinvented independently in 1955 by Crichton. They had a little fight of priority on this. Was then used by Crichton to make one of the great predictions of turbulence, namely the inverse cascade, into the because what they did is, all these people, they kept a finite number of Fourier modes, and then one can easily show, it's a bit technical but it's well known, that what you get is a finite dimensional dynamical system which is conservative in all possible senses. Not only does it conserve energy, but it conserves volume and phase space after you separate real and imaginary paths for convenience. And then you can apply Gibbsian statistical mechanics, and consider equilibrium distribution of the form e to the minus combination of whatever invariance you have there. That's pretty easy in 3 dimensions, where you have a single invariant, in the simplest case, non-helical case. But Crichton did it in 2 dimensions, when you have energy and entropy. It's not so trivial, and you notice there is a kind of Bose condensation, where you can have a lot of excitation going into the gravest modes. Grave, that means low k. This is a musical language. But he liked to use this language. He did play music. Yeah. About as well as his former advisor, Albert Einstein. That means not very which the inverse cascade was discovered. So from there on, that was, as you see, 1 year after Mandelbrot, myself, and others, we were trying to do something, got nowhere, but Krachmann did. And then in 1989, Krachmann went much further. In a paper written with Shi-Shen, there is a little sentence that nobody noticed. Particularly, I did not notice until about a year ago, because I have written recently a scientific biography of Krachmann with Gregory Ailing, which required rereading all of his papers. Some I had already read 30 times over, read them the 31st time, discover new things, etc. And this paper contained a sentence, of course I could attribute it to Krachmann and Shi-Shen, but I asked Shi-Shen and he doesn't remember anything of this, so I assume it's very much Krachmann style. The truncated Euler system can imitate Navier-Stokes fluid. The high wave number degrees of freedom act like a thermal sink into which the energy of low wave numbers excited above equilibrium is dissipated in the limit where the sink wave number are very large and the anomalous excited wave number. This dynamical damping acts precisely like a molecular viscosity. Nobody noticed that. But in 2005, there is a paper published in Physical Review Letters by these people. Scholar, the one I know best is Brache. I know everybody, but Brache has been a collaborator of mine. And what they did is a huge Euler simulation with 1600 cube modes. And what they discovered is that the high K modes quickly thermalize. They go into a kind of thermal equilibrium where the spectrum is precisely the K square we talked about. But it takes a very, very long time until this K square extends over the whole range of wave number. At first it affects only high wave numbers, in other words, small scales. And when you look at the effect of these thermalized small scales on larger scales, it's basically the same as if you had a molecular world, and you know what the molecular world is doing to us is it's changing our conservative Euler equation into a dissipative Navier-Stokes. I mean, this is exactly how Navier came up with this viscous term by considering molecules. He had very strange laws, Navier, in his first paper. He assumed that the interaction of molecules would depend not on their distance but on their relative speed and things like that. It doesn't matter. Whatever you put, provided you are not violating conservation laws and things like that, you get roughly the right for reasons of that mathematicians would invoke normal forms and things like that. But okay, this is well understood. So you can do all kinds of games, microscopic games. You can do so-called lattice gases where the microscopic world becomes Boolean. You can do thermalized things here. And it all seems to be giving at least roughly viscous ordinary hydrodynamics on large scale. This is a very strange thing because after all, we are I think all of us are in some way hydrodynamicists, whether or not we're involved in numerical. And we try to decouple to the real world. And therefore we say, well, there is viscosity and so on. If somebody completely removes all dissipation, say, okay, that may be an interesting mathematical game, but that's not the real world. The paradox is that if you remove viscosity, but you also keep a finite number of modes, then the real world comes back. It's very, but we shall see exactly how it comes back. That's the interesting part. So, okay, just mostly I'm trying to explain things in words and in pictures, but just in case you want to know exactly what I'm assuming mathematically, I'm writing a Q equation. This is the other equation, but I don't think that it requires much introduction to this audience. It could have been the MHD equation. It is sometimes convenient to write it in abstract form. We're just bringing out that both the nonlinear term and the pressure term are quadratic in the velocity, so one writes some quadratic form. I'm going to limit myself to the case of things that are 2 pi periodic in space. Now, the Galerkin truncation is something that is almost unavoidable when you're working with a computer, because those computers, in spite of Moore's law, they remain finite. You can't put more than a finite number of modes. Of course, you can put a lot more modes in 2011 than you could put in the 60s, for example, but still finite. So, Galerkin truncation is, as I use it, is defined as follows. You have a projector in Fourier space which kills all the modes for which the wave number exceeds some prescribed cutoff. The cutoff convenes I call K sub G, the Galerkin wave number. Okay. So this projector is denoted by P, and the Galerkin truncated hydrodynamical equation is just obtained by putting this projector in front of the nonlinear term and also taking an initial condition which is invariant of this projection, so which has only wave numbers lower than the Galerkin truncation. Now, this becomes a finite dimensional dynamical system, and just because things are periodic is therefore in the physical space, or in Fourier space, things are discrete. If you have a truncation wave number, there's a finite number of modes. Okay? That dynamical system can be described as suitable coordinates, which here are denoted y. They're related to the real and imaginary part of the Fourier components. And this was done for the first time by TDD. So one gets some kind of quadratic system of ordinary differential equation. And the remarkable thing is that it conserves volume in phase space. It's easy to show. It's a bit technical, but it's not. It's well known. And the real blessing is that the conservation laws, the quadratic conservation laws, are exactly preserved. Energy, entropy, helicity, I mean, depends on dimension, of course, cross helicity, whatever, are conserved. Therefore, you, as I said, you can play these games of Gibbsian equilibrium, and that was done by these people. Kreitner named these the equilibria, one gets this way, he named them absolute equilibrium. Now, the same game can be played on a much simpler equation. Burgers, actually correct pronunciation is Buchers, but I shall say Burgers. Burgers introduced in the 20s the equation that you know as a model of Navier-Stokes. This is a kind of poor man's Navier-Stokes equation. Then in the 50s, the interest in this model all of a sudden decreased dramatically when it was discovered by the same Hopf and also independently by Kohl case can be integrated explicitly. But if you do a Galerkin truncation of the Burger's equation, that you can't integrate explicitly. It's a much tougher problem. But it is defined just as before, so I'm not going to repeat this. Then there is an interesting question. If you take the Burger's equation, remove the viscosity, put a Galerkin truncation, and then let the truncation wave number become larger and larger, tend to infinity, as mathematicians say, does one converge in some suitable sense to the solution that everybody knows? You know, the solution that have shocks and things like that. It's not obvious, and there are other modification of the Burger's equation for which mathematicians have shown that it is precisely not happening. One is particularly famous. It is if you take the KdV equation. You know, the KdV equation is like the Burger's equation, except that you, instead of having a second derivative, you have a third derivative. Now, Lux and Levermore showed that if you put a very small parameter epsilon in front of the third derivative, then what you get in the limit when epsilon tends to 0 is not the solution of the, but some rather horrible beast that can be described. I'm not going to describe it, but it is not the zero viscosity limit. Mathematicians sometimes call it the entropy solution, but that's not a very good name for physicists. I wonder what they mean by that. So I call it the zero viscosity limit. And there are other instances studied mostly by Lux and his collaborators, other modification of the Burger's equation, which are energy conserving and which do not converge to the standard solution. So it wasn't obvious what would happen. So let me turn. Okay. Now, from now on, I shall start talking about tigers with a Y, and you will see in a little while, when I show you the certain poem, why they're called tigers. There is a strange phenomenon which was discovered by Brachet, unpublished, communicated privately to me, to Jean-Louis, etc. After having played with this monstrous 1600 cube Euler equation, he also played with the one-dimensional Burger's equation. If you can do 1600 cube, you can certainly do the Burger's equation. And he found something very strange. In the Burger's equation, you know, if you ignore viscosity, it is just a statement that each fluid particle keeps its velocity. So if you have something that is, if you have a fluid particle here, which is initially moving faster than one in front, it will catch up. That's a shock. You get a singularity. Of course, the appearance of a shock, it doesn't, they appear first with zero amplitude of the discontinuity, and it's the derivative becomes infinite. You get a cubic root behavior. It's called pre-shock. When you have that, you have infinite gradients there, and therefore you have a lot of high wave number excitation. If you have high wave number excitation and you put a truncation at some high wave number, you expect that things will be dramatically modified, and intuitively you would say, well, they will be modified in the region that are responsible for these high wave numbers, and that will be some kind of Gibbs phenomena, none with oscillations, not at all. Rachet found that the places where all the behavior started were not at all, this is the pre-shock here, this is an initial condition which is supposed to produce a singularity at time equal 1, you see here, and naively you would expect that some nerd due to truncation appears here. No, it appears there. By the way, this is shifted by pi over 2, because you will see here is a problem where we have interesting things happening both at the pre-shock and the distance pi away. If we want neither of them to coincide with one of the edges, it is simpler to do a little translation. Of course, the equation of translation invariant. This is just for graphical representation. So you see something appears here. What Rachet had actually seen was not as clean as that. He didn't publish it and so on. He had no idea of what causes this. And at first we thought about some symmetry, something. No, it wasn't that. Now I'm going to give you the key. It has to do with resonant wave-particle interaction. For anybody who is familiar with plasma physics, and many who come from Russia are, I can see some smiles there. One of the important phenomenon in plasma physics is if you have a wave, a traveling wave that has a velocity, and if you have a particle that happens to have a velocity equal or close to the phase velocity of the wave, then the particle feels the same pull over time instead of having a rapidly varying pull that produces the little ones that are averaging, and then you have interesting phenomena happening. This is what happens here, and it was discovered the following way. Chambry did experiments with initial conditions that are much less symmetrical than the one I showed you. You take, for example, 3 modes. You see, look at this. There are sine x, sine 2x, sine 3x. There is no particular symmetry in there. And such an initial condition, if you were to investigate the zero viscosity limit, then you would obtain several shocks, 3 shocks or so. And
what is kg?
Pardon me?
Kg is equal to 700. What should I think
Yes.
of that?
Yes.
What is that actually?
It is
What is it?
700. Yes.
Yeah, what is kg?
It is the Galerkin truncation wave number.
But I thought you go to 3.
Pardon me?
But I thought you go to 3.
To what?
3 modes.
No, the
condition.
initial condition.
Yes,
Yes.
yes.
Oh, okay. Actually, the calculations are done here with 16,000 volts
Yeah.
for a reason that has to do with graphical bugs that one otherwise sees. I think seem to be triple valued or something. So what Chomsky found is that these bulges, these tigers, appear at the places which satisfy 2 conditions. Condition number 1 is that the velocity should exactly match the velocity of a pre-shock or a shock. Condition number 2, that the strain in this region should be positive. You see, for example, these 2 places have a velocity that matches the velocity of the shock. You can see that very easily because you probably know that the speed at which a shock is moving is just 1/2 of the velocity immediately to the left and immediately to the right. And as you can see, these places are just facing the middle of the shock. But this point that has an x also, in principle, has such a resonant velocity. But the strain is negative. Now, why are only region with, I mean, there are two non-trivial questions. First of all, why isn't anything dramatic happening near the shock itself? And second, why is nothing happening at region of negative strain? Both have the same explanation. Now I'm just going to wave my hands. I don't want to throw too many equations at you. When you truncate a system at some wave number kg, then mathematically you have to use the projector that I showed you, which puts to zero the wave number. That means that you multiply by a gate, which is 1 here and 0. That's in Fourier space. In physical space, you have to make a convolution with the Fourier transform for such a gate. And as you know, it's something like sine kgx over x. The wider the gate in Fourier space, the more narrow it is in Fourier space. Therefore, you have these things, they're waves. They travel with the shocks. So here we have the waves, but their wave number is very close to the truncation wave number. Now look at what strain is doing to that. Suppose I have a wave here, and I put it in a strain, a positive strain, and I pull the wave out, its wavelength increases, therefore its wave number decreases, so it is safe for truncation. But if I put it in a negative strain, it's the other way around, the wave gets transformed into something that has a wave number greater than the truncation. It disappears beyond the horizon of truncation, as in a black hole. Now, at those places where a shock is forming, you have negative strain. And so these things act like black holes. They absorb the waves, and you don't see much damage there. So you have to find the suitable resonance point. All this, of course, can be made into quite systematic mathematics, but then it's rather heavy stuff, and it is better to read it in the paper. Actually, the paper, which is on the archive, is carefully divided into things that are explained in language close to what I'm telling you now, and then the more technical thing is in the last part. For those who say this is all a speculation, can you show this? Yeah. Now, let us see how such a tiger unfolds. For this, we subtract the unperturbed flow. I mean, the flow that we would obtain without truncation. Then the bulge, instead of being this way, is now flat. And you can see immediately that such a bulge shrinks in time. And that's easy to understand by resonance condition. There's a simple hand-waving argument. You see, if I give you all the hand-waving argument, it will take hours. So I'm skipping this one, and then it collapses. And after that, you begin to see some chaotic looking things. That's the beginning of thermalization. This is how thermalization, the phenomenon predicted by TDD, begins. And then, here, if you now look back, you will see these tigers growing in not only in amplitude, but in spatial extension. And if you wait, although they are born far from the shocks, if you wait long enough, they go up these ramps, so they go on the rampage, as we say, and eventually they will start messing around with shock. If you look here, you begin to see a very, very slight shift between the shock obtained, the blue one, and the red one is the zero viscosity. But it takes a fairly long time until here. Now, it's quite remarkable. The presence of these tigers is not, at least for a long time, not disturbing the shock. It is keeping them exactly where they should, in position, in amplitude, and even in law of coalescence. You know, when several shocks meet and they have certain law. Everything is just right. But you probably remember that real hydrodynamics is dissipative. Shock hydrodynamics is dissipative. Shocks dissipate energy. But this system, this truncated system, is energy conserving. So where is the energy going? Now, that's pretty obvious. The energy that is lost from the shock goes into the tigers in the form of short wavelength spatial oscillations. Then you can already guess that something strange could happen. Namely, if there is significant energy in these tigers, then there will be Reynolds stresses. I mean, a little while before we had Maxwell stresses. Okay, these are Reynolds stresses. If the Reynolds stresses are not strictly uniform, they will start moving the flow. They will drive it to an off state. And that is what is happening. The ramps that you normally get in the Berger's equation are replaced by these strange animals. And this is already an average flow by doing some low-pass filtering on the solution. So this does not converge to the shock solution. The shocks are okay for a long while, but these little monsters give trouble. And of course, one could ask, is there a way of getting rid of them? I'll come to that. First, I have promised to explain why the tiger. In 1794, so shortly after the French Revolution, William Blake wrote a poem which is a little bit too famous. Anybody who goes to school in an English-speaking country, that includes India to a large extent, has to learn this poem at a very young age, which people usually don't like, because it's a particularly difficult poem. It sounds very nice, but let me read just the first stroke. Tiger, tiger, burning bright in the forest of the night, what immortal hand or eye could frame thy fearful symmetry? At that time it was pronounced symmetry. What is this? Dozens of books and hundreds of papers have been written to trying to interpret what William Blake meant. There is mild consensus that what he had in mind was the symmetry between good and bad, good and evil, heaven and earth, and therefore from our point of view, conservative and dissipative systems. So you see why we decided to call this tiger. An additional reason is that Chomridi has actually made an encounter with the reed tiger, not in a zoo. So then rather quickly we tried to find out if this this phenomenon that we were able to understand and study on the Burger's equation, is it also present in multidimensional, incompressible hydrodynamic terms? That's a lot of change, because multidimensional and incompressible. The Burger's is highly compressible. So we did a fairly detailed study of two-dimensional, and we have done some limited study in three-dimensional. In three-dimensional, it's not published yet. The results are basically the same. So let me show you what's happening in two-dimension. In two-dimension, now you take an incompressible. You start, there's no forcing. You can do it with forcing, but it just messes up things. You start with a bunch of more or less random eddies, mostly at low K, and then you let the system evolve. And for a while, you see things that are boring because you don't see any effect of truncation. For example, here it is. What is shown here is the Laplacian of vorticity. Because if you show the vorticity itself, you will see the same thing, but you have to wait longer until you see it. So it's better. Now the important figure at time t equal 0.71 is this one. Here you have this thing, this cigar-like structure, is just one of the eddies that you had initially that has flattened by a well-known mechanism in two dimensions. And you begin to see tigers. Look, here. And if you look carefully, you will see that the tigers are taking place, are being created at places where the velocity is parallel to those cigars. You can check that by looking at the streamlines, the gray lines here. The places where the tigers appear are those where the velocity, which is tangent to the streamlines, is parallel to the cigars. But there is also a condition on strain again, more or less the same, some two-dimensional version of what I told you. And if you take point X, no tiger. It gets sheared beyond the horizon there. If you wait longer, then these tigers tend to become rather monstrous, and they're all over the place. This picture has the advantage that you can zoom it. Let me see. This is in, well, okay, no. It's in full screen mode, therefore it's not zoomable. But all the figures in the paper are fully zoomable because you have such a range of things, you know. And still we managed to have the whole paper with 52 panels, not exceeding 4 It's a non-trivial exercise in data compression. I mean, you can zoom this picture. I would suggest you take it from the web or from the archive, and then you will see. You can see all the gross details of what's happening inside the tigers. Okay. I just want to, before engaging the discussion, I want to mention that now our main effort, having more or less understood, I mean, how these tigers are produced, has become somewhat more practical, and we call it tiger purging. Tiger purging is the idea that perhaps one can do hydrodynamic, genuine dissipative hydrodynamical or image deceleration with no dissipation at all, using just Galerkin truncation, but doing something about the tigers to remove them before they have done too much damage. Now, during the last few months, we investigated that on the Burger's equation, not yet the two-dimensional Euler equation, and I didn't bring any slides to show you, but I can tell you it seems to work rather nicely, but there is again something very unusual. It is well known that there are all kinds of ways of filtering away the undesirable high wave effect in order to get genuine dissipative hydrodynamics. You can use this viscosity, you could use hyperviscosity, various filters, etc. But here, something different. Tigers in physical space appear at places that are rather remote from the fine-scale structure that you would have without truncation. In Fourier space, they are high K animals, because you see this oscillation has very short wavelengths. And they appear in a boundary layer in Fourier space just below the truncation wavelength. But not immediately. It takes a while. One can study, even not just numerically, mathematically, what produces these things, and one finds that the early stages of tigers, before they have the shape that you see, there is an input in Fourier space which affects not just wave numbers near the truncation, but all wave numbers. It is strongest near the truncation, but it falls off as you go away from the truncation to lower wave number. It falls off rather slowly. So there is a kind of noisy input which affects huge range of wave number. If you try to figure that out, you can't, because you would throw out the baby with the water. The baby is the correct aerodynamics. But if you're patient, you wait. Very well. Then you will see that the tiger is reorganizing itself into a genuine tiger, which is concentrated in the boundary layer by a non-trivial phenomena involving the non-linear term. It is understood 90%, but that's in section 3 of the paper. And then you can perch. But you have to be not perched at each time step. That is a disaster. If you perch at each, for example, suppose the maximum wave number is 700, and suppose the tiger is mostly lying, say, between 650 and 700, and you perch at each time step. This basically is the same as if you were to put the truncation wave number at 650, and you would get new tigers. You can purge away these large 50, but not too often. You have to fine-tune this. Okay. This is something that we are exploring at the time. So it is just mentioned as a research program in the paper. And to give you an idea of timescales on this, human timescales, this work was started. Between the time the work was started and the paper was put on the archive, there were 3 years, with 4 people working a lot. This is it's not super fast activity, but now I think we can turn to questions. I'm ready to hear your question.
Axel?
There's a distinct non-locality. The tigers appear non-locally.
You mean Fourier non-locally, or physical?
Physically non-locally.
Physically. Away, yeah.
Yes.
They appear resonance points.
Also in 3D.
Also in 3D.
Or 2D. And what I was wondering is that your purging may not be accurate, may be too rough.
By purging simply just for high wave numbers?
Actually, it seems to be working. Originally, we had another idea, and we didn't call it tiger purging, but tiger abortion. And use wavelets and detect the tigers and then kill them before they have a a chance of growing to serial sizes. But then we found it is very complicated, and the other method is much simpler and works very nicely.
Yeah, I mean, the resonance, you talked about resonance, but what do you have explicit evidence which warrants the name resonance? I mean, why is it really a resonance? I mean, I see that
it's the way, I mean, you know, the Burgers equation, and to a large extent also the multidimensional Euler equation, you have particles which, except for pressure effects in them, keep their velocity. And if that velocity matches that of these what we call truncation waves, I mean, I can make a full mathematical theory of this truncation wave. It is not trivial, and I don't want to give up. And then one can make sense precisely of this thing. But that we did only after we were fully convinced that this is exactly where things happen. And it took us a long time until we had the right theory. But you can read it, the theory.
Yeah. If tiger phenomena is related with resonance,
Yes.
particles and waves, is it possible to describe this phenomena in kinetic language?
Yeah, but I mean, it is. There is even a discussion, the paper of similarities and differences with problems, for example, in Landau damping or so. When we were trying to develop a theory, we tried all kinds of methods. One of them is a Gabor transform, which gives the equation almost a kinetic aspect, but it turns out that other methods work better, but that's one of the possibilities.
More questions, please.
So what's interesting about what you talk about this the phase space, this Galerkin projector method. So it looks to me that it's very similar to what people do in renormalization group analysis, where they first throw away the high frequency modes from the system, and that has a feedback in some renormalized quantities, which takes into account of the fact that some modes are not longer present in the system. But what you have done is simply to have a cutoff in the high frequency part, and no discussion about the feedback of the missing modes in your system. And I think this should be taken into account in some way.
I just skipped heavy theory because I didn't want to write too many equations. But it's definitely not skipped in the paper.
So if you throw away one mode from your equation, how is the feedback of this mode taken into account in your formulas?
I can answer, but I will become a bit technical, if you don't mind. At least I will not write on the blackboard. I will. There is the method to do theory is a perturbation method, where one compares the solution U without truncation with the solution V with truncation, and then one can basically by subtracting, it's a little bit more complicated than that, one can obtain an equation for the perturbation, a nonlinear equation for the perturbation, which has new terms. There is an input term that comes from beating interactions of things which are beyond the Galerkin truncation thing, and it is this beating interaction which feeds the tiger, but it feeds them over a very wide band of weight numbers, and then it's the interaction of that with the basic flow by an effect which resembles what one has in the Orr-Sommerfeld dynamics, which reorganizes it into a boundary layer.
So you really have an effective theory for the low energy part.
Yes, of course. I mean, generally, I hate publishing purely numerical papers without a serious attempt at understanding. In this case, we were a bit frustrated because we understood only 90%, not 100%. So, but 3 years had elapsed, so we decided to publish with 90%. But the paper makes it very, very, very clear what we do not understand.
So there are last very short questions.
Yeah.
You had one.
Yeah, I just wonder how the tiger depends on your time integrator.
On the what?
The time integrator.
The time?
Time integrator. So you need to evolve.
Of course. This is a problem where you have to be very careful about, we generally use fourth order Runge-Kutta, and we've checked. I mean, we have done thousands of calculations, but we have done dozens of checks with higher order, high precision, etc. So we are dead sure that what we report is not at all affected by time matching, by the time matching scheme. I mean, don't forget that one of my favorite games is the study of singularities, and when needed, I'm not afraid of working with 100 decimal digits and high-order Taylor method and so on. So this is not terra incognita.
Well, thank you very much for the participation. So, the last talk before we go for lunch is by frisch+chan, local anisotropy in MHD.
Can people hear me okay? Okay. So I have to say it's pretty scary to speak here because we have so many experts here, both on numeric and turbulence. So I guess before I start, I should say this is still work in progress, and your comments are really welcome. You cannot see too well, but this cover page here is actually a volume rendering of magnetic energy in a turbulent flow. And you can actually see some structure here is pretty anisotropic. So I guess so I guess today I want to try to make some sense of this. Now, of course, energy turbulence itself is really interesting, but let me still put up my own motivation for it. So what you see here is an image of the galactic center. So you see a lot of different features. So let us zoom into this bright source here and look at it at a different frequency. So this is is the source, the radial source, and these are actually different stars orbiting around that. So using these orbits, we are actually able to calculate the mass of this central object. Turns out it's like 4 million solar mass. So this is the super black hole at the center of our own galaxy. And now, if we look at it at another frequency again, we will focus on this source here. You see it become brighter. So once a day, our central black hole actually become brighter. There's flare appear. And now if you do your light curve with the flare, then you see this kind of oscillation. So people actually associate this with a 17-minute period. And that turns out to be the orbital period of the innermost stable orbit of the accretion disk around the supermassive black hole. So the hope is that if we understand this oscillation, maybe we can say something. Maybe you can say something about general relativity and do some great science about it. So myself has done some numerical modeling of Sagittarius stuff of the central black hole. So this is an MHD simulation, and then we use frisch+chan radiation to calculate how things emit around the black hole. So this is the accretion disk. And again, you can the picture doesn't show up too well, but you are able to see some feature around here. So surely the MHD turbulence is not isotropic. And the hope is, if we understand this feature, maybe when we are able to image the central black hole, we can actually measure its inclination. Okay. So that simulation I showed you is it's just not well resolved. The resolution is too low. So when people study accretion disk, we also do local simulation. So instead of doing the whole disk, we take a small piece, and then we do a local simulation. So this is one such example. This is a local sharing box simulation. At the beginning, we only do really weak magnetic field, and the system is unstable. The magnetic field grows. So this is the infamous Melito rotational instability. This is the channel solution. It's actually an exact solution to the nonlinear system. And then later on, the channel solution breakdown, we are in the turbulent state, and this turbulent state gives us the radial stress, Maxwell stress, and transport angular momentum. So Christian people really care about the transport of angular momentum. So I'm just writing down the equation for the angular velocity, and that's the turbulent viscosity. The stress, turbulent stress. So is a difference between the radial stress and the Maxwell stress. And sequentially, I've actually proposed using the alpha parameter to prescribe this term. And let me also write down the mean field MHD equation, the mean field induction equation. So this is dTdB, dE is the mean field, and we have our EMF. And if now you compare them side by side and you find out although the physics we care are different. So dynamo people care about how to generate magnetic field. Christian people care about how to transport angular momentum. But the basic principle are really the same. Okay, so you also see some anisotropy in this stream box simulation. And actually, Charles Garvey, who actually tried to plot the correlation. So this is the correlation of the magnetic fluctuation. You can see it's along in this direction. So the MHD turbulence in a shear box is also anisotropic. Now let's go back to this image again. But this time, let's focus on this feature here. If we zoom in, we see something like that. So it's so-called the galactic center radial arcs. So without too much imagination, you can actually associate this with the sun, the magnetic loop on the sun. So the point I want to make is when we study MHD turbulence, we really should think about the anisotropy in the turbulence because they really give us the feature that we can see. Okay, so the anisotropic of MHD turbulence comes from the magnetic field because there's no way we can transform away the magnetic field. The mean velocity we can just carry that using Gaussian transformative that way. But magnetic field we cannot do that. And because there's a mean field now, so MHD turbulence we can consider that as a collision of Alfvén waves. And if now you think about this, the guitar, then you can see it's really difficult to twist your string in this way. It's actually pretty easy to rearrange them. So that actually gives you the physical picture of the anisotropic cascade. Okay, now this is just the scaling law that I'm pretty sure everybody knows. This is the energy spectrum. So it's the energy. C is the Alsace variable for each k, and then you just per k. And this is the energy cascade rate. So it's again energy divided by the time scale. So in strong MHD turbulence, which we mean here, there's strong interaction. And the cascade time scale is just your energy at the wave number times the wave number and then inverse. So that gives you a time scale. And you put this into this formula, and you find out C here actually proportional to k to minus 1/3. And then you put that in, and then you find out this scaling law. It's pretty standard. Now, however, if we have weak turbulence, then when the Alfvén waves collide with each other, you do not deform that in a single time scale like that. You actually need to wait for random wave to collide. So you need to put in this extra chi-square here to get a correct scaling. So after you do that, again you put in the equation, then you can find out another energy scaling. This is also another standard thing. So this is just a table that I copied from Axel's review article. So it's the strong turbulence that I described, and also the weak one. But in the case that, say, your kinematic, when your magnetic field is actually really weak, your MHD turbulence can become isotropic. So at that time, you just say your parallel K and the perpendicular K are equal, and then you get another scaling, which is this one, K to minus 3/2. Okay, so now we have this different scaling for different kind of MHD turbulence. So it's now time to actually look at the simulation and try to find this scaling. But there's a problem because say you have a strong background field and then you have your Alfvén wave, because the field line are actually wandering around. So if you just use the naive FFT to calculate the anisotropic spectrum, you won't be able to find the correct scaling. So what Cho and I actually don't know how to read that name. So what they propose to do is you need to apply filtering to your system. So instead of just doing FFT, you take your four-way space, you apply a cutoff, and with the cutoff now you have a mean field. And with the mean field now you can define parallel and perpendicular direction. And then you use that, then you can calculate the correlation. And so this is their result. What they show is if your cutoff is at a pretty small k, so you have really weak mean field, then you're not too isotropic. But when your cutoff is at a higher k, then your small scale actually they are more along the mean field. Okay, so this is pretty useful, but you can also see the problem because when you change the scale of your cutoff, you actually have different plots. So it's difficult to see using a single plot what is going on. So I'm trying to propose something different here. And the thing I'm proposing is called the anisotropic energy budget. And it really comes from the cumulative energy spectrum. So the cumulative energy spectrum just integrate your standard decay up to K. And with that, so now let's consider again a cutoff scale. So this is one plotting is the contour for magnetic energy. So on the left hand side I have the mean field, on the right hand side I have the fluctuation. When I change my cutoff, you can see I put a lot more energy to the mean, and these are all fluctuations. And if I do that, then this point start to make sense. So you cannot see too well. So this line here is actually the cumulative energy, both for the magnetic energy. So it's both the parallel and perpendicular component. But at each cutoff, you can actually have different contribution. So that's total energy of the mean field. And for the fluctuation, you can have some contribution from the, I think this is perpendicular component and the parallel component. And you can do the same for the kinetic energy. So this plot here is just the energy budget from 0 to 1. I'm just plotting how much energy contribute when I shift my cutoff. Do people follow me? Okay. Now, if this is the cumulative energy spectrum, when I take the derivative, I will get the normal spectrum. So I can do the same thing for these components. Take the derivative, and I will get spectrum like that. So the red lines here, again, corresponding to the magnetic component. That's the total energy. That's the perpendicular contribution, and that's the parallel contribution. And the white lies there for the kinetic energy, and they have the same meaning. So after I define this plot, I can, so these are actually the contribution that I just told you. So after I define these lines, then I can start to do something interesting and look at my simulation. So I'm using a spectral method. So again, Gallatin truncation. So without viscosity and sensitivity, you can actually show that the system conserves energy. And you can actually show that, how do you call that, is the thermodynamic equilibrium?
You will see very clearly how the thermalization spreads to lower rate.
Yeah, and you actually get K square spectrum. So this property actually is really nice because it allows me to do an extremely high Reynolds number simulation with not with a small resolution. Of course, you will ask how good that is, but the nice thing is at least I can tell you that the worst case is my simulation is under dissipative. So maybe you will dissipate enough energy, but I don't need to worry about the numerical instability or things like that. And because I'm actually going to show you decaying turbulence. So once the turbulence starts to decay, I'm pretty sure I'm fully resolved before. And this is this plot here, I'm actually plotting the energy. So it just show you the energy is conserved really well in the core. And my viscosity is still above 0. Okay, now let me do a MHD simulation with. I'm pretty sure the Reynolds number is like 10,000. Magnetic Reynolds number is 10,000. And I put up the background magnetic field equal to 1. So maybe I can visually move it again. So you can see the turbulence start to decay, and because of the strong background field, the turbulence became anisotropic. And now I can apply the method that I proposed. The anisotropic energy budget. So this is again the energy budget. I cannot see any of it. That's too bad. And I take the derivative of this plot, I get a spectrum, and then I can also plot the ratio between these different energy contribution. You can actually see, well, yeah, it's just too bad. But so the magnetic ratio is around here, and this is for the kinetic energy. So you can actually tell when the background magnetic field is strong, you have a lot more energy in the parallel direction. So in some sense, it's giving you the cost immediately. Now let me decrease the background magnetic field a little bit. Do the simulation again. You can still see the anisotropy feature. And let me do the energy budget plot. And now you can see in my small scale, I can actually have a lot of energy going to the perpendicular direction. So this is actually the anisotropic energy cascade. And I can decrease the background magnetic field again. So this look more or less like anisotropic turbulence. So if we look at the energy budget and the ratio, this is pretty much between 1 and 2, so this is more isotropic now. And when I decrease that further, now I'm in the isotropic phase, and you can see this is not giving you too much anisotropy. So so I guess what I already show you is with a really simple how should I call it? So I introduced this anisotropic energy budget, and I think it should be a really nice method to look at anisotropy in energy turbulence. And I also show that when your turbulence is strong, your anisotropic cascade actually gives you a lot of energy in the parallel direction. If you just look at the spectrum, you cannot find that. So I think this is something interesting. And since I have time, maybe I can also show you this skip copy. So this is again the ratio when I change the Prandtl numbers. So you can see when you change the Prandtl number, because turbulence are different, so you can also get different things. But because now I'm just using decaying turbulence, so you may ask, when you change the Prandtl number, are you still looking at the same time scale? Are you comparing apple to apple? So that's actually something that I still have to work on. So yeah, I think that's pretty much what I have.
Very good. Questions, please? So, may I ask you a question? So, do you confirm the spectra people get from these analytical models? Because I couldn't see any powerful low inertial parts in the spectra you showed.
Yeah, so
Even
because
though your resolution is very high, right?
no, my resolution is not high at all. It's only like 256.
256.
Yeah, so for power law, I would say I really do high resolution. But at least the phenomenology, the direction of the cascade seems to be correct.
There was also much controversy about how it was called, not detailed balance, but between Sridhar and Sergei Nazarenko.
That part I actually haven't looked at it in detail.
It would be interesting to have a look,
Yeah,
right?
yes.
Axel?
Critical point.
I can't remember how it was called, not detailed balance, but what?
Do you have spectra of versus K-perp and K-parallel in particular? Because people have been saying that the numerical simulations, even though one is thinking they actually confirm what Sridhar, they still show K to minus 3 halves power spectrum. And there's various reasons why this could be. One could be that MHD turbulence is much more non-local and may then be affected by the cutoffs on both ends of the inertial range.
So at the moment, you can tell I don't have any power logic. So I couldn't really look at the answer.
But if remarks with these three halves, it would be interesting to have a simulation, not with homogeneous field across the whole box, but a large-scale field with 2 or 3 cells, or well, a significant number of cells within the box. Because creationist model, he wasn't thinking about an absolutely homogeneous field. It was a field which can be in loops, large-scale loops, but still a significant number of them. Then all of a sudden you can have this isotropy at larger scales.
Yeah,
Because of this no-local layers.
and I should also make clear that the method that I propose here, it actually works when you don't have a large scale field. So when you have loops.
Yeah, I think that is perhaps the most interesting cases where the field at large scales is still generated by small-scale dynamo action in the separated regime. Still have power then at large.
Anyway, non-trivial field at the large scale. Okay. Questions, please questions. Or
But do you have in mind the local cross-silicity? Yeah, why is that important? Because of the imbalance, yeah? The local imbalance.
yes,
But you only have local, so the global cost is zero.
thank you. Really very session and all speakers in the morning, and enjoy your lunch.